So I want to give a theorem of Buium's that's kind of useful in Diophantine geometry, and I'm going to give the baby version of this theorem. It says the following, and this is from the 90s, the early 90s, and this is due to Buium. And it says the following. So here's the setup. So let K delta be a differential field, be in C ring. Let's say, how did I do it? D1. So this is this is the dual numbers. So these are rings with derivations. So we have this category of rings with derivations, and let's suppose that K is characteristic 0, and we have the following. So if X over K is a smooth projective, and then let's say the genus of X is bigger than or equal to 2. If the Kodaira-Spencer class associated to this derivation is non-zero, then this implies that the first jet space of this twisted tangent space is affine. And so this thing is going to live in H1 of X with the relative tangent sheaf here. Okay, so this is the theorem. And it tells you when the first jet space is affine. And it's important that this is for curves. Okay, so the trick is to find a nice presentation. Of the first jet or prolongation space of J1. All right. And so here's how we're going to do it. So to find the presentation, we're going to look at this Kodaira-Spencer class, and this is an H1 of the tangent bundle. Of course, this thing represents torsors, or so we have these torsors, and we can associate cohomology classes to this thing. And this is isomorphic to the extensions of O of X by T of X over K. So this is just kind of a general fact. And then by duality, we also have a canonical isomorphism with the cotangent sheaf, extensions of the cotangent sheaf by the structure sheaf. Okay, and so what this gives us now is an actual extension up to isomorphism of extensions. So we have this E here. E is going to be a vector bundle on X, and it's going to be an extension of omega by O. So we're given this E, and now I'm going to tell you what the nice presentation is. So the lemma, and I don't know who this is due to. Maybe I think it was first used maybe by Grauert. I'm not exactly sure. If you know who this is due to, you can tell me in the comments. So the first jet space, okay, here. So this is the twisted jet space where we're considering this derivation on the base is isomorphic to the projective bundle of E with removing a divisor here. And this divisor is actually going to be equal to this projective bundle of omega X over K. Okay, so this surjection here is actually going to induce a closed immersion of this into this. Okay, and this equality here is as T of X over K torsors. That's the idea. And okay, so this is the presentation here, and the idea is. Well, let me just say what this thing is. Here. Again, so if let me just for a reminder, so we recall first that this thing here for some abstract vector bundle, let's say f So this is this global proj of the symmetric algebra of F. This is going to be some space over F, and this is actually equal to, okay, so I'm going to use a different notation. We'll call this P of F dual. So we'll have this thing, and then we'll have this guy here. And the physical thing of this is the space of lines of F bar over X. So again, here you'll have, so we have X here, and you know, X could be actually, this is completely general. It doesn't need to be a curve or anything like in the statement of the theorem. But here, so you over each point, so we have maybe a family of these, this family here, and this sits over this. So this is what P of F dual looks like, and so this is saying that these are the lines in F dual. Okay, so and then the blackboard P, this denotes the proj construction, and this is this part is this is the notation they use in EGA. This is what Fulton prefers, for example, in his intersection theory book. And then there's always, people are always switching between these two things. So when you see a blackboard P, they could mean one of two things, either this or the dual, and that's that. Okay, okay. So that's what this is saying. So really, again, if we go back to this thing, in this particular case, this would be this would be P of the tangent bundle. So this is the space of lines of the tangent bundle here. Okay, so the geometry is kind of related. You should be thinking more about the tangent bundle than this thing. Okay, so we have this presentation here, and what we'll want to do is we'll want to show that this is ample, so that we'll be removing essentially a hyperplane section from projective space. So this is embedded into projective space via some embedding, and then we remove this ample divisor. Well, this is like removing a hyperplane at infinity, which will make the whole thing affine. And that's the idea of the proof. So we need some criterion for, we need to get a D, which is this thing, to be ample on PE. And so to do this, we're going to use a theorem of Gieseker. And so this is in his P ample bundles paper. This is maybe theorem 2.2 of this paper, and it says the following, and this theorem is strictly about curves, and this is the point where the proof breaks for trying to do it in higher dimensions. But if X is a smooth projective curve, and let's say that F is ample, so this is an ample vector bundle. Okay, this also needs to be over K. The characteristic of K needs to be 0. So let's say it's over a field of characteristic 0. And it says for every a non-trivial extension, let's just say not for every non-trivial extension of, let's say, F by the trivial bundle is ample. Okay, so in particular it says that if we, so let me just write it in notation now. If we have something like this is non-trivial. This non-triviality condition will come up from the non-triviality of the Kodaira-Spencer class in our application. This is E is ample. Okay, so E being ample, we'll recall that this means that that O of PE1 is ample. Okay, and then it'll turn out that that F will be in the linear series associated to this, which will also make it ample. And that's kind of the idea. Okay, so that's the idea. So now I'm going to kind of let me just say one more thing. Okay, so the idea is that projective space, so this is kind of, or some projective bundle, is really affine space union a hyperplane at infinity. And then removing this, gives you something affine. That's kind of a weird way to write something, but this gives you something affine. Okay, so this is the idea. I'm going to end the video here, and then in the next video, I'm going to give the proof. Thanks for watching.